Hi and welcome to the lesson of multivariable calculus. In this class, we are going to talk about line integrals in a space, right? So let us recall the notion of the ordinary integral. So what do we mean by an ordinary integral is that if we have a curve and we are just considering the area that is bounded between this curve that is given by f of x and this x-axis, then we usually use the notion of the ordinary integral. That is, if we want to find this area, then we say that this is integral f of x dx over this a limit on the x-axis, that is, say, from a to b. Now, the line integral is a generalization of this ordinary integral. For instance, if we have a line in a space, for instance, we can draw it here. If we have a line in a space in XYZ coordinate system, for instance, this is Z, this is X, and this is Y, and we have a line on this space, for instance, this line, and we have some curve or some function defining this curve, say f of x comma y, and then we want to compute the area bounded by this curve over this line. Then we use the notion of line integral, and we say that we are going to integrate the function that is f of xy over this curve c, right? So now C may be a straight line or a curve. So it depends on the context of the problem, right? So let us consider this problem that we need to compute the line integral, and the function is given, that is 4x z plus 2y dx. And we have to compute it over this curve C, and it's given that this C is the line segment from 210 to 402. So we have a line segment, and we have to find the integral over this line segment of this specific curve that is given by this equation, right? Now, what we need to do is, first of all, uh, where we are going to integrate this function over this curve C. So since it is in space, so we need to parameterize this curve in order to find the limits of this integral. So we already know that how to find the parametric equation of line, since we have these points that the line contains. So if we have the points, then we can simply find it by this relation: x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct, where ABC is the vector that is parallel to this line that contain these points, right? And this ABC can be found simply using this relation, that is this vector. Let's say this is q and this is p. So simply q minus p gives this vector that is parallel to this line, right? So q minus p means 402 minus 210. So we get to -1 and 2. Therefore, the parametric equation of this line is going to be, let us assume that this is P naught. So therefore, P naught equals 210. That is x naught, y naught, and z naught. Therefore, this becomes 2 plus 2t. Then y equals 1 minus t, and z equals 0 minus 2t. Therefore, these are the equations for this line. So this is the parametric representation of a line in space. Now, the other thing we need is that the limits for this parameter t. And now we can see here that the point is the initial point, that is 210, and the final point is 402, for instance. Then we need to find the limits of t. Therefore, just assume the value of t that will give x equals to 2, that is this initial point. So this is at t equals 0, and then we need the point 4. So we need to choose such value of t that gives this point 4. Therefore, we can choose it as 1. Therefore, we can write that t goes from 0 to 1. So this is the limit of this parameter t, and it works for all the uh, dimensions, that is x, y, and z. And we can just verify that if we put 0 here, we get 1, that is this one, and then we put 1 here, we get 0, that is this one. Similarly for z. Now this is a parametric form of the line, that is this curve C, and then we have this limit. Now we can simply write this integral in form of t. Therefore, it will be 4 times x is 2 plus 2t times z, that is negative 2t, and then we have plus 2y, so times negative 2t plus 2 times 1 minus t, and in place of dx we can find it from here, the relation of dx and dt. If we differentiate it with respect to t, we get 2, that gives us dx equals 2 dt. Therefore, it is 2 times dt. Then take out this 2 and just simply multiply. We get 8. uh, 4 times 2 is 8, times negative 2 is negative 16t, and then negative 16t squared plus 2 minus 2t dt. Now, by simplifying this relation, uh, we will, okay, one thing that one mistake here, this is not negative 2d, but it is positive 2d, since this is the positive 2, right? So this is the vector ABC. Since the vector C is positive 2, so it will be positive 2d. Therefore, this thing here is positive, which means that these are positive. And if we simplify this expression, we are just going to get 16t squared plus 14t plus 2 dt. Now, if we now we integrate this function, and that is in terms of t, and we will get the solution, that is 86/3, which gives the this line integral over this curve C, that is parameterized by these equations, right? So let's take some more examples on this topic. And now let's see here that compute the work done. Now this is an application problem of the line integral. So compute the work done by the force field, and the field is given here. That is F equals 4y, 2x, z, and 3y. So it's a vector field acting on an object as it moves along the helix, defined parametrically by these equations. So the parameterization is already given, and we have a helix. So a helix looks like this. So we need to find the work done by this force field along this helix, right? So the parameterization is given. Therefore, we know that work done equals F dot dr, which means that where dr is dx, dy, dz, right? So dr is the small length, it's small arc length we can say on this helix. Let's say this one dr. So it has all the dimensions, that is x, y, and z, because it is in a space, right? So this dr represents the vector dx, dy, dz. So f dot dr, it is the dot product. Therefore, we can take the dot product of the function f with dr. So now this becomes 4y dx plus 2x z dy plus 3y dz. Now this is the function that we need to integrate over the curve, and the curve is this helix, which is parameterized by these equations. Now that is x equals to cosine t, y equals to sine t, and z equals 3t. Now we can verify these parametric forms over these limits, and the limits are given, that is from 2, 0, 0 to -2, 0, and 3 pi. Since the x value is 2, therefore if we put 0 here instead of this t, in place of this t, so what we get is x equals 2 cosine 0, that gives us 2. And if I put uh, pi here, that is cosine pi. So since it's going from 2 to -2, which means that I need -2 here, therefore cos of pi is equals to -1. Since I put pi here, therefore I'm going to get -2. It means that my t goes from 0 to pi. Okay, and these other forms y and z will also satisfy these interval. That is, we can see here y equals 2 sine t, so y equals 2 sine 0 gives 0. So we can see that the y direction is going from 0 to 0, and y equals 2 sine pi again gives 0. So this is also verified, and for z equals 3t, z equals 3 times 0 gives 0, which is 0 here, and it's going from 0 to 3 pi. So z equals 3 times pi equals 3 pi. Now since this is the limit for our parameter t, now we can compute this integral by this parametric form, 2 sine t and z equals 3t. Therefore, we have 4y dx plus 2x z dy plus 3y dz over c. Now we need to express this in terms of t, so 4 times y is 2 sine t, and dx, for dx we need to differentiate this with respect to t, so we get dx over dt equals -2 sine t, which gives dx equals -2 sine t dt. So we have -2 sine t dt, and then plus 2 times x is 2 cos t, and z is 3t, and dy is 2 cos t dt. Therefore, we can write 2 cos t dt. Right, then 3y, which means 3 times 2 sine t, and this dz will be dz equals to 3 dt. Therefore, we can write 3 dt. Now limits are from 0 to pi. We can take this dt outside, and then we can just simply simplify this function and integrate, which is already shown here in the solution. So this is the simplified form, and then we arrange all the terms and integrate, and we get this result, that is 36 minus 8 pi plus 6 pi squared. So this is how we compute line integrals in space, and that is the generalization of the ordinary integral that we use to do over the axis, that is either x-axis, y-axis, or z-axis, right? So hope you guys understand this lesson. Thanks for watching the lesson. That's all for the time being.